Visit Soligo.com
Okay,
to get
let's start.
started.
So, a car with a mass. Now, I'm going to be noting down some information as we go through this question. So, a car with a mass of 16...
Teams that use Monday.com to manage their work save time and money. Here's why. The average team spends 5 hours a day just staying updated. That's 12 hours per department, per company, a day, a week, a month, a year. That much time costs this much money. But with Monday.com, it's totally different. Don't wait for updates. See what your team, department, and company are working on. One place for all things work. The big picture or the bottom line. Even work that's not on Monday.com is now on Monday.com. Your meetings, feedback, docs, it's all here. So you'll never have to say, where do we stand with again? How much time and money can Monday.com Work OS save you each year? Click here and find out.
Per hour. To get from kilometers to meters, I need to times it by 1,000. 1, 2, 3.
When
meters
picking your U and your
per
DV
hour
for
means I need to
integration by
multiply
parts,
it by
the handy
60 to get
mnemonic
to
tree
minutes,
member is
and then by 60
LIAT,
again to get to seconds.
which stands
So
for
on the bottom,
logs,
I've got 60 times
inverses,
60. That zero
algebraic
knocks out that
expressions,
zero.
trig
That zero knocks
expressions,
out
and
that zero.
exponentials. And so the idea here is
divided by
you let
36,
U
which gives you
equal the
25
first
meters
thing
per second.
on
Now, for the
this
other
list
one,
that shows
it's
up
going
in
to
what we're
be
trying to integrate. So let's see how that works.
57.6
So in our first example here, we have x to the
times
fifth
1,000
ln x. So
divided
x
by
to the
60
fifth
times
is
60,
algebraic in
which is going
nature,
to leave you with
whereas
576
ln x
divided
is
by
logarithmic
36,
nature.
which will give you
And
16
so for
meters
u,
per second.
we're going to pick
Now I've
the
got everything in the
logarithmic
units that I want.
expression.
We
We're
can
going to
start
pick the
going through with
natural
our
log.
calculations.
And our
So
dv
force
will
is
be
equal to
everything
mass
else,
times
will be the x to
acceleration.
the fifth
In this
dx.
case, our acceleration
And then
is
we can
just
continue
this one
on
with the x
from
with
there,
the 2 little
integrating.
dots. The mass is
So
1600.
let's go ahead and run through this one real quick.
Is
So
equal
du
to our
will
oppositional
be
force
1 over x
minus
dx.
320
V will be
root v to the power of 3.
1/6
Now, the
x to the
first trick
6th.
that you might find is not
And so
expressing
we'll
that
get
correctly.
u times v
That 3 is there over 2. Remember, this has a little power
minus
of 2.
integral of
If I
v
just did that, that would mean it was
du.
a to the power of a half. So that's how
And in
you know
this
that that would be
case,
a 1 and that would be a 2.
one of these x's will
Alright,
cancel
so
with one of
next thing I'm going to
those,
do, I'm going to
leaving
find an
us with
expression for
something
the
we can
acceleration.
integrate. So we have our original 1/6
Divided by
integrating x to the
1600.
fifth, we get another
Now
1/6.
that will leave me with negative
And there's our antiderivative. Okay,
v to
and
the
so
power
there's the
of
first
3
example.
over
Let's
2
take a look at the next one.
over 0.2.
So here we
now, the
have
next thing that I'm
sine
going to do
inverse
is
of
I'm going
x,
to
which
start
is
looking
an
at which
inverse
function for
expression,
acceleration is going to make the
and
most
then
sense.
dx,
Now up here
which
I've
is
still
our
got things in terms of
algebraic
v,
expression
and now
here.
I'm looking
So
for
in
them
this
in
case,
terms
we
of
would end up
time, so
letting
that means that I'm
u
going to be
equal
expressing this as dv
sine
over dt.
inverse.
The problem I've currently
dv
got is
would
if I
equal
take this t to the other
dx.
side,
So then
then
du
that's
would
not
be
going to be deriving
1
with
over
respect
square
to
root
the
of
same
1 minus
variable.
x
So I need to flip both fractions.
dx.
So
And
dt
v will be
over
just
dv
x. So then
is
in
equal
our
to
integral, we have u
negative
times v
0.2 divided by v
minus
to
the
the power
integral
of
of
3
v
over
times
2.
du. And then it turns out that
Now let's
this
just double check
integral we
some
can
things to
do
make sure we're on
using
the same
basic
page.
substitution.
That would turn
So if we
into
let u equal
that's
1
good,
minus x squared
which means that...
du negative 2x dx, then
Hold
this
on a
will
second,
become
I've made a mistake somewhere.
negative x over root u times du over negative 2x. The x's cancel, so we end up with positive 1/2 integral of 1 over root u.
Here, this
Remember,
part
1 over
here.
root u is u to the negative
Alright.
1/2, so the integral of that
Let's
will
just
be
fix this up.
u to the positive 1/2 divided by half.
Okay, so this is going to
we'll have
become negative
positive 1/2
0.2. And then when I flip
times
my
2
fraction,
root
it'll
u.
be 1 over
Back substituting, that would be
negative
a square root of
0.2 v to the
1
power of
minus
3
x
over
squared.
2.
So putting
So
that
now
back
I can
together
take
here,
this
we
to the
have
other
x
side,
sine
dv,
inverse of
cancel
x
him out, and then I'm going to integrate this side.
plus
So first thing I'm going to do is
this
I'm going to remove
root
this, and I'm going to
1
make that
minus
derivable.
x squared
So that'll become
plus
negative
c
1 over 0.2.
as our integral
On this side, we've got
of
dt.
sine
We're
inverse.
integrating with respect to v
All
to
right,
the power of
so now
3
let's take
over
our
2,
next
but it's negative
look at our
because
next
it's in the
example here.
denominator. with
So
respect
here
Okay,
we
so
have e
keep
to the
going
x,
through.
which is
When I integrate
exponential,
this really
and
has a
sine,
1
which
there.
is trig.
That's how dt
Since
is
trig
allowed to
shows
stay
up
there.
first on
When I
the
integrate
list,
that, it'll turn
we'll
into
let
just
u
t.
equal sine x,
Then when I integrate this,
and
remember we're
dv
adding 1,
equal
so this will
e to the x
increase to
dx.
v to the power of
And I'm not going to
negative
show
a
that one the
half.
rest of the way
And then
through
I'm going to divide it
in
by
this
negative
video.
a half.
For the
Meaning
next one, we
the
have
fraction
x,
will flip and I'll be left
and
with
x
negative 2
is
over 1.
algebraic.
I'm not going to
e to
write
the
that
x, which is
because it's
exponential.
going to take up
Since
space.
algebraic
Okay,
stuff shows
multiplied by
up
the
first in the
constant in
list,
front.
here we'll let u equal x.
Okay, so now
and
when these
dv
two multiply, it'll
equal the
become
e to the
positive.
x
That will
dx.
cancel out with that.
In the last
So
example here,
I'm
we have
left with a
x
function
squared,
that
which
looks
is
like
algebraic,
this.
and
T is equal
cosine x,
to
which is
0.
trig. So we'll
1
let
over
u
0.1
equal
v
x
to the
squared,
power of negative a
and
half.
dv equal
Or I could
cosine
express
x
that as
dx.
1 over
All right, so that's how we can use
0.1.
LIAT to help us
And on the
identify our
denominator,
u
I'll
and
have
our
the square root
dv
of
in
v.
integration by parts.
So, now that I've done that, I can find the time taken for the speed of the car to be reduced to this. Now, I am missing plus c on the end.
This is the most dangerous problem in mathematics, one that young mathematicians are warned not to waste their time on. It's a simple conjecture that not even the world's best mathematicians have been able to solve. Paul Erdős, a famous mathematician, said, "Mathematics is not yet ripe enough for such questions." Here's how it works. Pick a number, any number. 7? Good choice. Okay, we're going to apply two rules. If the number is odd, we multiply by 3 and add 1. So 3 times 7 is 21, plus 1 is 22. If the number is even, we divide by 2. So 22 divided by 2 is 11. Now we keep applying these two rules. 11 is odd, so we multiply by 3, 33, and add 1, 34. Even, divide by 2, 17. Odd. Multiply by 3, 51, add 1, 52. Even, divide by 2, 26. Still even. Divide by 2, 13. Odd. So we multiply by 3, 39, add 1, and that's 40, which is even. So we divide by 2, 20, divide by 2, 10, divide by 2, 5. Odd. Multiply by 3, 15, add 1, 16, divide by 2, that's 8, and then 4, 2, and 1. Now 1 is odd, so we multiply by 3 and add 1, which equals 4. But 4 goes to 2 goes to 1, so we're in a loop, and the lowest number is 1. Now the conjecture is this. Every positive integer, if you apply these rules, will eventually end up in the 4-2-1 loop. This is commonly called the Collatz conjecture after German mathematician Lothar Collatz, who may have come up with it in the 1930s. But the problem has many origin stories and many names. It's also known as the Ulam conjecture, Kakutani's problem, Thwaites conjecture, Hass's algorithm, the Syracuse problem, and simply 3n plus 1. Why is 3x plus 1 so famous?
Among professional mathematicians, maybe it's not famous but infamous, in the sense that if someone actually admits in public that they're working on it, then there's something wrong with them.
The numbers you get by applying 3x plus 1 are called hailstone numbers, because they go up and down like hailstones in a thundercloud, but eventually they all fall down to 1, or at least we think they do. You can think of the numbers as representing the height above the ground in meters, so a number like 26 would start 26 meters above the ground, and if you apply 3x plus 1, it rises up as high as 40 meters, and in total it takes 10 steps to get to 1. So 10 is called its total stopping time. But take the very next number, 27, and it bounces around all over the place. In fact, it climbs all the way up to 9,232. As an altitude, that is higher than Mount Everest. Before it too falls back to the ground. In total, it takes 111 steps for 27 to get down to 1 and end up in the 4-2-1 loop. The paths that different numbers take vary so widely, even numbers right next to each other. So how do you even start to make progress on this problem? Well, honestly, mathematicians struggled.
People just decided that this was something invented by the Soviets to slow down U.S. science, and it was doing a good job at it because everybody's sitting there twiddling their thumbs and making no progress on this trivial thing that you can tell school children.
Jeffrey Ligarius is the world authority on 3x plus 1.
The first time I met him, I was a senior in college, and he pulled me aside and he said, don't do this.
I think I'm going to let
Don't work on this problem. If you want to have a career,
t plus 2
do not start
equals
spending time writing
Therefore,
about this or publishing any papers about this.
dt.
Do real math for a while to
1.
establish yourself.
Alex
now I'm
Kontorovich
going
didn't
to
listen.
have
He and Yakov
100
Sinai looked at the
over
paths of the
the
hailstone
power of
numbers.
-2.
Were there any patterns? Well,
Over
obviously all of them end up
the
at 1, but
u.
what about the paths they take to get there? The pattern
So
is
this will come
randomness.
down.
Here is the sequence of a large number chosen at random.
Now I've got
The graph
100
peaks and then
over
drops so low that you
-1
can't really see what's
u
happening at this scale.
to the power of
But if you take the
-1
logarithm, you find
c
this wiggly graph with a downward trend.
equals
It looks kind of like the stock market on a bad day. And this is no coincidence.
displacement with
Both
respect
are
to
examples of geometric
So
Brownian
now I'm
motion.
going to substitute
That
some
means
stuff
if you
in
take the
to make
log
it
and
make
remove the
sense.
linear trend, the fluctuations
Let's
are
write
random.
this out nicely.
It's like flipping a coin each step. If the coin is heads, the line goes up. Tails, it goes down. 3x plus 1 is just like the random wiggles of the stock market. Over long enough periods, the stock market tends to trend upwards, while 3x plus 1 trends down.
Power of -1. So
Another way to analyze 3x plus 1 is by looking at the leading digit of each number in a sequence. Here are the hailstone numbers starting with 3 as the seed. And we can count up how many numbers start with a 1, how many start with a 2, how many start with a 3, and so on to make a histogram. We can do the same thing for the sequence that starts with 4, that's a short one, and for the sequences that start with 5, 6, and 7. Again, for each sequence, we're just counting up how many numbers start with each digit, 1 through 9, and adding that to our histogram. If you keep doing this for more and more numbers, eventually the histogram settles into a stable pattern. For the first billion sequences, you'll find 1 is by far the most common leading digit. 30% of all numbers start with 1. Around 17.5% start with 2, 12% start with 3, and the frequency decreases for higher digits. Fewer than 5% of all the numbers start with 9. Now this pattern is not unique to 3x plus 1. It actually comes up everywhere, from the populations of countries to the value of companies, all the physical constants and the Fibonacci numbers, just to name a few. The distribution is known as Benford's law. And it is even used to detect fraud. If all the numbers on your income tax forms obey Benford's law, then, well, you're probably being honest. If not, you